Okay, cool. I think let's start. So, just a brief introduction, and then we can just start and dive in. And I'll just introduce about the topic, not me, but yeah, the topic that we're going to discuss more about in this session is about um, cloud databases, right? Cloud or transactional databases, which is another kind of realm altogether, and kind of a complicated realm, I would say. It's not easy to build databases that also provide all these constraints that a transactional database has, and also be scalable, and also performant enough for the use case. So yeah, the talk is kind of more specific to how Amazon Aurora cloud native database is being built, the design of Amazon Aurora. However, to jump into that, before jumping into that, we require a lot of basic knowledge and understanding of databases in general, how the storage looks like, how the computation is happening on databases, how transactions are managed, all of. So the whole presentation of the talk, essentially, a lot of it would basically be understanding the fundamentals of it, fundamentals of the database, fundamentals of how the storage looks like, how it all works, and then we will go into parts of the design of Amazon Aurora, which is basically the cloud native scalable solution for that relational databases. Um, so yeah, let's dive into it. And yeah, so in general, we'll just start with a basic introduction of relational databases. Um, what's a relational database management system? It's basically a kind of a database that allows you to build relationships by defining those relationships in a way that basically represents the real world relationships that you would want to kind of build. So essentially, and also does it in a way that it's structured. So you can just create a simple table, and you have multiple tables, and all these tables can be related in some way or not, depending on how you build it. But yeah, the relationship database basically allows you to manage your database data and also relationships around the data. And it's like an entities relationship that you can build in a relationship database management system. And that poses kind of a challenge, right? As you think, like, relationships are constraints. Constraints are need to have a lot of other constraints itself will require you to build systems that handle those constraints. And when you have constraints, it's not easy to also build scalable systems. So we'll go into deep dive into more about understanding how all of this works, and how we can scale, how the current the current tech ecosystem around relational databases is kind of amazing, and how it's growing as well, and how it's scalable. So yeah, the relational databases kind of handle structured data. As you can see, I have also tried to make sure, by the way, all the information on the slides. So when I share the slides, maybe later, if some of you need slides, last time I was asked multiple times about that. So you can just use the slides to kind of for your offline knowledge. Um, so yeah, I have added all the data, but yeah, basically it allows you to have um, queries on top of the data that you want, and those queries also allow you to kind of manage relationships and build data out of the build the view of relationships in um, form of table structure. And that query language that it is basically, that I think I would assume most of you would know, is SQL, which is like a gold standard query language for relational databases, for data retrieval, update, insert, delete, all of that operations. Just an example over here, as you can see. Um, yeah. So what are the core features of RDMS? Uh, One thing, of course, as we know, the data grows, the company size grows. Um, you would need to have a scalable system. The volume of data is also growing. So you will see even in later in the slides as well how the scalability aspects hurt us in some sense, and how the whole solution around Aurora kind of comes into be as a natural progression towards scalability, and not really an overkill solution just for showcasing the tech, the amazing architecture that they have built. So yeah. For data volumes, security, of course, we need security. We need to have access controls because primarily a lot of companies' data is the source of most biggest vulnerability. So yeah, we need security, consistency, following the asset properties that we'll dive into it a bit down as well. Um, Ease of query with SQL. I think this is kind of a lot of aspects of our day-to-day lives. Engineers, non-engineers go into kind of identifying what data you need, identifying building relationships in the data. All of that is not easy to do that unless you have a very good interface. Just like ChatGPT allows you for having simpler interface to interact with all the knowledge base that you would want to interact with, or Google search doing it as well. You need a good layer of interaction and interface, which SQL does amazingly well. Of course, it's also being a part of like multiple. It's been for like multiple decades that it's been used, so that is also kind of evolved into really a base level query language for every RDA of course, there are variants of it, but yeah. Coming to asset, right? We do know that asset properties um, uh, are essentially the constraints that I was talking about earlier. So yeah, the properties are essentially atomicity. We need all the changes that we do should be atomic. I've given an example over there, which is one of the classic examples in a banking system. You would need to have atomicity if you're kind of crediting and debiting an amount in particular in a particular transaction. So you need to have atomic transactions so that when you roll back, it kind of there's no inconsistent state between, right? Consistency again kind of follows through is you need to have some as I mentioned from relationships. When you build relationships in a relationship database, you also define constraints, right? And those constraints need to always be consistent. So if one of the relationships says I belong, or I am a child of this parent, for example, and the parent says no, that whoever is saying that it's not my child. So that's an inconsistent state, right? And therefore you will require a lot of lawyers and legal issues you go into if that happens in real world, by the way. So it's similar to have it in databases. You wouldn't want inconsistent state because that's essentially your a kind of a debugging nightmare. Isolation. So one isolation is it's kind of a very key component when you do querying or reading stuff, right? You need to kind of isolate with the other aspects of when the concurrent, essentially when you're reading stuff, you don't want your read to be affected by other aspects of operations that database kind of offers. So if the database is writing the table and you're reading from table with a different row, for example, you don't need that write to kind of impact your read ability. Or even if it's the same row, you need to define the isolation levels for it. And we'll again dive into it a bit later in the session, what it means. And we have a lot of slides to go through, so I'll probably be a little bit quicker in the earlier slides. And durability, yeah, it's basically the term what it says. We need to have our systems always available, durable. Even if they are not available, we should not lose data, which is again a primarily security concern. If we lose some data, it's a security nightmare. It's essentially dollars. You would start losing money, right, as a company if you're using it and you lost your database. So this asset we've discussed about it. How does it compare against like a different set of consistency model? Excuse me. So there is another kind of similar design model around databases is base, which is basically available, soft state, and eventual consistent, right? So what it basically says is that it guarantees that the data that you need will be available without promising the actual consistency in like real-time consistency. Like when you make a change, you need to kind of see that reflect directly. That is not guaranteed in systems that follow base architecture, which I'll give an example of as well. And then we have soft state. So soft state is a system kind of may change over time, and might also it's kind of in a way where you do not have constraints set between in some cases the data that you have, there is no constraint, so there might be not be the exact state that you see is consistent with the the application relationships that you have built with the data. So an eventual consistency is, like as I mentioned earlier, eventual consistency and the acid like consistency is a bit kind of what it says is that you will not have a consistent state when you require it to be, but it depends on how you've configured your database system. And the database will kind of make sure that it is eventually in the final state would be consistent, but there is no guarantee that it will be consistent whenever you require it to be. Because of, again, aspects of scalability. And so it's a trade-off, right? And the trade-off kind of comes with real world use cases. Like, for example, you have social media platforms. Like, you don't need your feeds to be always consistent. Let's say me and my friend both are following the same people. Sometimes I might not see the person's update, because like it's still not updated on my end, right? Because of because the data that I'm kind of querying as in my application is going through might not be in the current consistent state as my friend's application is going through. So yeah, it's not required, like in state, right? Nobody cares, right? And eventually I will see the update, so it's kind of fine. There is no business impact, nothing like that. Sometimes also, like depending on high volumes during like high e-commerce sales, you also don't need like real-time consistency as well. So it's like a trade-off. Again, depends on business case, depends on use case. There is no right or wrong here, acid or base. It depends completely on your business, your use case, your domain, all of it. The other aspect that kind of boils down to is CAP theorem, which states that, and as I was discussing about it as well, is a distributed system cannot simultaneously provide all three. Like it's kind of, as I mentioned, the trade-off, right? You cannot have 100% availability, partition tolerance, and 100% consistency. You cannot. That's the theorem basically, and depending on your use case, you choose the databases that provide the two of them, right? So yeah, that's pretty much the CAP theorem, and it's very important theorem, by the way. Follow through a bit to understand it a bit in details. So the next slides would basically be around RDBMS in general, because the talk is around RDBMS, and it's going to be just to kind of go towards Aurora's design. We need to first understand a bit about, in general, how the database internals look like. So we will go into a little bit of, I wouldn't say there's a lot of deep dive into it, but a little bit of the internals of databases, relational databases in general, and more specifically, just to kind of keep it simple to understand, because it's a kind of highly used database, which is Postgres or MySQL. So most of the examples or anything that I would be showing, and the configurations or anything that I mentioned would be around these two databases, but they do kind of apply to a lot more other databases like MySQL Server, SQL Server, Oracle DB, all of it. But yeah, just a side note. So yeah, fundamentally, database systems use concept called page as their fundamental storage system, right? Storage mechanism. So pages are like a unit of data storage. Excuse me again. Unit of data storage that allows a database application system to kind of fetch or write data to it. And that is the fundamental data unit of data storage, and there is no lower level than that for a data storage system. And configurations depend on how much you want to have a number of rows in a page or not. Depending on that, the configuration can be managed, but typically it ranges from 4 KB to 16 KB. And yeah, the page kind of the data in the page basically represents the rows, right? In most cases, right? Again, in most cases, always 100% is not always something that, because there will be some weird database system that might not be doing it like this. But yeah, in most cases, like MySQL or Postgres, this is how it is. and the page is like a fundamental unit of data, um, for storing rows, right? And again, it depends, because there are some database that allow for column-based storage and some database to row-based storage. But yeah, in general, it doesn't really matter from our doc point of view, sessions point of view. It's essentially page that stores the data that you would query to fetch, and that's the one thing that it always needs to fetch. So going to so out of page, it comes down to an upper level. How does page kind of is stored, right? And one of the databases, which is Postgres, uses a heap storage mechanism, right? And what heap storage mechanism means is, just think about as a disk. In a disk, uh, the fundamental data structure, how it's represented as a heap, and the heap is essentially an unordered way of storing pages. There is no order in it. So you can have fast insertion. It's kind of allows you to have new data being updated faster. If you have write-heavy system, it works better in these cases. In some of the cases, of course, depends on how you configure it or what's the size of the database, all of it. But also it leads to slower read performance because it's not contiguous blocks in some cases. So we know disk storage, or at least traditional disk storage and not SSDs, allow you for that don't are not great at random access. And contiguous blocks kind of are significantly faster. So that is something that heap storage is not optimized for, and Postgres is not even going for that. But of course, there are other aspects where Postgres shines and MySQL doesn't work. Like, just as I mentioned, fast writes, for example, right? It doesn't need to keep in order. Alternative to another kind of storage, which is B-tree. And B-trees are ordered storage, or B plus trees, I would say. Like, that's the modern version that MySQL uses. And B plus trees are kind of modern way to store pages of data for InnoDB, like MySQL databases. And what it does is, essentially, it keeps the pages on the leaf nodes, and it's structured. So whenever you want to insert, whenever you want to fetch, you would basically follow the B plus trees consistency and B plus trees fetch algorithm, which allows you to kind of fetch it in order. And that's the fundamental data structure as well. And it serializes on disk similarly. And this is how InnoDB stores its pages versus heap storage. As I mentioned, PostgreSDB does it. And yeah, and also just kind of highlight, there are other variants of Postgres as well that might switch storage systems. That is because it's open source. There are some variants that might also have different side of. So just to kind of clarify, it could also be in some cases where it also uses clustered index and not for main storage, and not non-clustered index as secondary index, which I've kind of showcasing here. But it also means that if you want to kind of improve reads, it's slow, right? You would assume that because it's a heap structure versus a B plus tree might it would be faster. So that's why Postgres offers, or even MySQL offers, alternative to kind of have a faster query, is having a index. And index is again a B tree index, which you can define your which you can kind of define your data on, the actual data that you would want to query on, and it allows you it builds a pointer to that data in the heap in case of Postgres. And of course, in case of MySQL, for example, over here you can see, in case of MySQL, which is just on the right, it points to the actual primary index, which is a clustered index, which is the actual, it holds an actual data, actual row pages in that. Versus in case of Postgres on the left, it's in heap, it's unordered, and all the secondary indices or index point to the actual row value referenced by the heap pointers on the disk. So that's how it looks like. And yeah. So the very next kind of understanding that we would need to do is, how is how is it physically stored, right? So data in the database is stored in disk in form of files. As we know, it is kind of depending on the storage as well. If it's SSD, it has a different structure of storage, but in general, all of it is blocks, right? And the blocks are kind of and then abstracted in terms of files. And yeah, so as you can see, the data files contain actual data pages, including heap organized data or tree index organized data. The log files, which is a very important aspect that we will also kind of dive into for Aurora's design, by the way, is the transaction logs. And the logs are essentially append only files that are also stored on disk for durability purposes, but they essentially hold data for consistency and durability, and allowing you for any cases when if there's a crash or something. And also kind of makes things more really fast. That makes the database systems much faster than just traditional writing on disk. And then temporary files, some for cache purposes, fast querying purposes later on if you want to use more aggregation or something like that, materialization, etc. So and then the next part comes is the OS file system, right? And depends on OS to OS, depends on how you also would want to use the file system. But like for example, a traditional Linux-based file system has all the inode structure, and it kind of the application that in case of database management system would use this interface to access these files, right? So that's how it works. And yeah, it depends on file system to file system, but more or less it's something. It's an interface that allows you to access the data that we mentioned earlier on the disk, right? Yeah, accessing data, as I mentioned earlier, file system interaction, the database interacts with the OS, right, in general, and OS then calls, OS uses its own file system interface to kind of access the disk for open and closing the files and all of it. And yeah, it translates to high level operations into kind of low level disk operations I mentioned earlier. Disk IO operation, depending on disk, how it is, but basically the IO works on reading and writing blocks of data, and that translates into abstraction of, as I mentioned earlier, on B trees in terms of heaps. It translates into heap structure, which translates into pages, which is the fundamental data that a database would understand. The buffer cache. So these are like, again, we don't need to go into too much details of it, but this is how these are important aspects what databases actually use to optimize for performance. And they use buffer cache or operating system buffer cache, and this operating system uses it to handle frequently accessed data, but also database management systems also optimize for this. And depending on, again, OS, which is more in most cases Linux systems, they allow you for far finer grain optimizations for using buffer cache and leveraging the buffer cache, as we'll see how it is being used, in fact, in Aurora later on. Database buffer pool, this is application level. So like if you were to have your own application, let's assume you are building your own database. Hello? So yeah, sorry, I guess there was a little bit interruption. All good. So we have database buffer pool or a buffer cache system that, again, you if you were to build your own application, you would want to have some caching system to optimize for, again, for reads. So it also caches frequently accessed pages into the application level memory, and yeah, just for performance reasons. So how does the typical read flow look like? This is as simple as just when you read is basically reading, parsing the query. So this is all application level. Again, very important to understand what is application level, what happens on the application layer, which is a more stateless layer, and then happens on disk or on storage system, which is again a stateful layer. And this is where, again, this is very important to understand to kind of go into why Amazon Aurora is highly scalable. Big reason why it is because these two are decoupled in a way. Spoilers, but yeah. So how it looks like is when query parsing and optimization, it does query when you select something, join with something, it does an optimization depending on how you define in your index, all of it. It's smart enough to understand what's the best way to kind of fetch this data. If, depending on if it's in the cache, fetch it from the cache, all of it. For sorting purposes, using file-based sorting, or use memory. When if you have a lot of memory, just use memory, just pull all the data and do sort in memory, which is much faster, right? So all of that is application deciding what to do based on its own configuration and understanding of what system requires and what system resources is available in general, which the application would continuously talk to OS to get that information, right? Then there's data retrieval. As I mentioned, if the data is available in memory, in buffer pool, the page itself, the data itself, you don't need to go to the disk. Disk is slow, just fundamental fact of life. Disk is slower than RAM, right? Concurrency control, this is really important. And just so, if I'm going a bit faster, sorry about that. I'll share the slides if you want, but we have a lot of slides to go through. Still 15 more to go. So yeah. Concurrency control, we need isolation between reads, right? As I mentioned earlier, it is really important to have isolation. If you read something, it needs to also not be affected by other person reading something, or other person writing something, or other transaction, other threads, or other process, all of it. So fundamentally, it's very important to build systems that are they are thread safe, kind of handle concurrency better, and basically database systems, the current database systems like manage it really well. So they provide multi-version concurrency control in some cases. As I mentioned, in Postgres, it allows for faster writes in some cases. So you can kind of, for isolation purposes, you can read a version that is not really the version that that is currently written by a write operation. So that's the multi-version, really, just to make it faster. It creates a snapshot of data with a version X, and then there is version X+1 that's being written, but it's still not committed. So the read thread doesn't need to care about it, because it just needs to get the current data and fast enough, right? And it's presented how based on the UI and the interface that you would use. So yeah, read isolation. Before accessing the data pages, depending on the isolation level, again, the database system, the application kind of checks for multiple areas of it checks that it runs, and depending on what isolation level it is, if it's commit isolation, if it's uncommitted isolation, if it's no isolation at all, just read whatever it is, it's 30 pages, all of it. You can just it make sure that all of it is consistent and provides data, and based on after the reads is done, it would just keep all the it would just remove all the logs that was acquired, and those are read logs essentially, and not write logs. In most of the cases, I would assume that's how most of the database would do. At least Postgres and InnoDB does it. And once its operation is completed, the read logs are released and transaction is considered complete. And how this typical write flow look like? Of course, it's a bit different, right? The writes are more complicated. So when a write operation is done, database kind of modifies the relevant data pages. It pulls the page first if it knows that page needs to be modified. If it's an update operation or something, then the row is updated, the page is in memory, changed, modified, and then it logs into the transaction logs that I mentioned earlier. The transaction logs are append only, and we'll come to that to ensure durability. So let's say the disk somehow crashes, for example, or the OS crashes or something, and you do not have any information of what was written. So for durability purposes, what's the most fastest way to track what was done by the application is to have an append only log or append only file, which is, as I said, fastest way to kind of write something that is durable and allows you for recovery purposes later. So that's how it's done. Concurrency control, depending on, again, how your write operations look like. Most of the cases, because of RDBMS, it needs to have tighter controls around writes. And depending on how you define versioning as well. you would either use pessimistic locking or optimistic locking, depending on use cases. Uh, Most of the cases, pessimistic locking. Then the data persistence. So this is one important aspect, is that after you write to the log, it doesn't immediately write to the disk. In most of the cases, you can configure it to have a synchronous write. So every write basically would commit to a disk, but it's not done that in the majority of the cases. At least the default configurations are not like that, and it builds the buffer, and then it has a periodic flush. So just for performance reasons, so that disk is slow. First of all, it impacts CPU. It's high IOPS heavy, so you would want to kind of make sure that you don't continuously write for every write operation. If you're write heavy application, you would just kind of you just have you lose a like basically have you have to put in a lot of money to build a vertically strong scaled system, and yeah, it's not scalable in general. And also from a database point of view, they are also already the managing the writes. It's durable. The val logs, basically, which is what we were talking about, transaction logs. Um, uh, it's fast, super durable, so you don't need to kind of get this fine grained synchronous writes to be done, which is slow. Yeah, so the next one is transaction commit. This is again application level. Transaction is not something that a storage system knows about. Storage system doesn't care about it, right? But an application level, you need to have this as the atomicity and consistency guarantee that it provides. So once it's done, it would basically commit the transaction, basically write to the append only val log, transaction log, I mean, and then it would just say it's done. You can move ahead. And then later, sometime later, when the buffer is flushed to the disk, sometime as in that time, again, it is depending on some configurations of your database, it writes to the disk, and the disk is in the nearest update state. Uh, all of this is really important as we go to Aurora's design. Yeah, so I think basically I covered most of it, but I think it's more of a repeat of how the transactions look like. They acquire exclusive locks depending on the row locking or table locking system. In most cases, it is row locking system. Then the changes are logged into a transaction redo log. This redo log, this is important. It depends on system to system. MySQL has a redo log as well as bin log. Postgres also has redo log, and I believe it also does logical replication and not physical replication, but I'm not fully sure about that. I think, but yeah, I'll probably add some references later on to kind of check for yourself. But for MySQL, I'm kind of pretty sure it has bin log and redo log, both of the. Yes, so after the modifications successfully applied, transactions may be committed, and yeah, it's if the transaction fails, if something happens, if your application made some inconsistent reads or something, and the transaction basically is no more in a correct state, or the data is not in the excuse me in a correct state, then the transaction is rolled back, and yeah, that's how the transaction. That's all application level system. So okay, so this is the part where I was basically talking about, which is the val logs or write ahead log system. It's a protocol. Actually, it's not really a log, more or less. This defines like the fundamental reason behind why the current modern databases are durable, consistent, and super fast. Right? Like it's a really really important concept. And it's not, by the way, just kind of a note. What we're talking about is RDBMS, yes, but val logs are not just a kind of applicable to RDBMS or relational databases. If you were using, let's say, some NoSQL database, I would name them because I don't really know which one would be having it. But NoSQL database, like, for example, MySQL, MongoDB, which is a NoSQL database, it might also be doing for durability purposes write ahead logging. But yeah, so that's something that just to kind of make sure that we are not just on track, that this is only done by RDBMS and not some other databases. Most of the databases offer this protocol, but in different variants. So as I mentioned earlier, this logging is really, really key to durability as well as performance, because it makes sure the data is consistent, as well as it doesn't need to go ahead and continuously write to the disk. Doesn't need to flush to disk because it's aware of what exactly happened at what point in time, and it's super fast because it's append only. Just again think of contiguous memory, contiguous blocks writes that I mentioned earlier. On even on traditional hard disks, that is 10 years old or 15 years old, contiguous writes is going to be extremely faster, significantly faster than any random reads or writes. So that's the power of write head logging protocol, and there are different variants of it, different ways of implementing it. One is redo log, which is it maintains the kind of, it creates a kind of a unique identifier in as an offset, and provides what exactly was modified on which disk block needs to be modified, and all of that kind of record is being added, which the queries and all of it around it. And so that in case of, let's say, a crash or a failure, the system can go back to the state. Let's say if it wasn't written to the state, it can go back to that state and roll back to it, or roll in forward to that value. And it also allows for point in time retrieval, point in time rollback. So if your system becomes corrupt due to some changes, if your data becomes more corrupted or something, you would want to go back point in time into something that was consistent. So this allows you to do that, and it's super fast. So that's the design overall of the system, kind of ensures for faster recovery. So yeah, now that we have discussed a bit about RDBMS and hope and sorry, just one second. Yeah, I was taking the time. I'll discuss the we now have a bit of understanding of how database systems or RDBMS looks like. And we can see like there are some limitations to it, right? Like we mentioned about writes, the write locking, consistency. With constraints, you cannot trade off. There are some trade-offs that you have to make sure that you cannot scale, you cannot easily. So you can see there's a it's limited to vertical scalability in some aspects, because you can only write to one system, and because you need to have a consistent system. If you write from a multiple system or multiple servers, then it can potentially have a negative effect on your consistency, right? So it's single point failure, limited availability. It's difficult to achieve high availability in some aspects, because again we have this constraints of consistency and isolation and durability and all of it, and atomicity. And there are performance bottlenecks, of course, as I mentioned. If you cannot scale, these are the bottlenecks, right? If you cannot easily scale horizontally. Geographic distribution, again, because of single point of failure, you cannot have writes distributed to multiple systems, and that it becomes a kind of a potential disaster that can happen if a region goes down or something like that. So yeah, these are the basically limitations of single server systems. So one thing that we discussed about, which is var log, which was this one. This is kind of leveraged in and used to replicate data between multiple systems. So to build a highly available, scalable systems, replication is one way to do that. And what replication does is that, of course, the name says that you replicate some data to a different server, and now your reads can actually scale, and you can read from multiple servers. And how would you replicate the data? There are multiple ways to do it, and depending on also types of replication, which is synchronous and asynchronous replication, as you can see, there is one way multi-way replication, depending on the database as well. Mostly in case of RDBMS, mostly it's one-way replication. And there is so synchronous asynchronous replication depends on how the system is defined. Aurora does it, as we'll see later, asynchronous replication. And in cases of in some database is where like RDS, it uses synchronous replication for consistency purposes. So yeah, this is basically how vals are shipped. And so as I mentioned, there are different ways to replicate. There's a physical replication, which is basically telling what exactly was changed, and kind of provides the lower level information about what exactly was changed, which block was written, which page was written, all of it, versus a logical replication, which kind of gives you a abstraction of what needs to be changing. It doesn't tell the replicated server, the server that is going to replicate. It doesn't tell what it needs to do. It just tells it a high level overview of what was the operation that was performed, and then the replication server will do its own logical steps to get in the consistent state as the main server, or the basically in case of master slave configuration, right? So that's how these differences are. uh, Postgres does logical replication. Don't fully quote me on that, but as far as I have an understanding of Postgres, it does logical replication. SQL, MySQL, it's in InnoDB, it does physical replication on bin log and redo logs, as mentioned earlier. But yeah, feel just have a bit of research done after this and just read through a bit to understand how each of this replication looks like in variants of databases. But in general, the concept behind it is how what I mentioned earlier. Um, yes, so as we discussed, we can scale, right? We can have multiple servers replicate, and yeah, that's the best way to scale. And we are now in a in a very highly scalable system, right? Not really. That's what Amazon will kind of come in and tell us, that it's not the most ideal way to scale. There are other potential bottlenecks, which of course, as we know, even when we did this horizontal scaling of reads, there is a bottleneck of IO, right? In the end, the read will also, depending on, let's say, one of the node being slower to replicate, then that node is in inconsistent state, and that is again, from an asset point of view, a disastrous state. um, so if one of the node has a slower disk or something, it has some problem with OS's firmware, all of it becomes again inconsistent, which is completely not against the principles of RDBMS, right? Or constraints that it sets. So as I mentioned, like, the bottleneck is still going to be there, and that's the IO bottleneck that there is a solution to it, which Aurora comes in and provides, and it moves the bottleneck from storage system to network, and then we'll see how it also optimizes for network, um, which is its design. But yeah, so uh, in traditional RDS, sorry, let's start to check time. Yeah, I think this. Hopefully, this is clear. I'll have to move a little bit quicker. So yeah, as you see, RDS PostgreSQL, it's the normal master slave configuration on Amazon Aurora system. You can see the architecture is a bit different. There are storage nodes, and there is a compute layer. The compute layer is a stateless layer that I was talking about, the one that it processes the query, converts the queries into more optimal queries depending on the index and all of it. And the storage nodes are Amazon's own proprietary design of storage that it has built around databases, and that is separated or decoupled from the compute. So now, if you think about it, the stateless system can scale, and a storage layer which can also scale as per Amazon, and with high durability, that becomes the system becomes more scalable, more performant. You can kind of build durable applications on top, right? Far more durable applications than you would be able to do it before. So yeah, how does it do it, right? Like, before going into it, we need to understand what exactly the philosophy of design was, right? And I think we kind of touched a bit, is that for online transaction databases, we need to also have consistency, but we also need to overcome the IO challenge that we have even with master slave configuration and replication. So what Amazon has done is it has a very fast shared storage system that is durable, right? And it has a systems of stateless EC2 instances that can connect to that storage. And there, in the database in general, themselves provide this system of um, actually recovering from a state, which is redo logs or not just recovering, but also tracking the transactions, right? Tracking the state of changes of updates and inserts and delete operations. So that's like Amazon leverages this database inherent ability to track the transactions and track the logging of changes, tracks the changes, I mean, and also it's scalable storage and puts the all of it to a network. Um, that network is now the bottleneck and not IO, because they are aware they can scale their storage system. They have multiple AZs. It can be scaled up to like 6 more replicas, and it will automatically scale to it. And when you let's say, and when a new instance of database for us kind of a slave that you would want to replicate, that you want to create, that slave can just directly connect to the existing storage system without, because it's on the network and not really connected physically in a disk somewhere in the server. Since it can connect easily on the network, you just build a highly scalable point in time data system that is also consistent and also leverages the inherent ability of replication, which is the redo log, right? So that's the beauty of the system. From a high level overview, how it does it, a bit, we'll go into details a bit. But yeah, it kind of leverages this storage system that it has built. It's robust. It's super fast. It has its different set of engineering. I would say, let's think about it as from a team's point of view. Has a separate team that manages its whole system, the whole storage system. They have SSDs. They research about SSDs. They they build OS level system calls that are faster, that make the calls faster, all of it. So it becomes like a highly independent, super fast scaled team that manages clusters of data. Um, so the how it works is that it builds this availability zones, and the storage system has availability zones just like EC2 instance or stateless servers would have, and it builds like a quorum mechanism. So it tells, you know what, I will write to the storage system, and sorry,
For this way.
any questions? Hello, I guess Sahil, can you go on mute?
Sorry about that.
Yeah, let me. Okay, so yeah, the as I was saying, like it has a quorum system where it would know what was committed at a point in time only when 4 out of 6 nodes say that they have the current consistent state. So it kind of has a majority kind of voting system where if majority votes that they are okay, it is okay and is significantly faster. All the read replicas can read the current state, and yeah, that's pretty much it. It goes. It can go on with the synchronous operations that it was doing. It can continue with the synchronous operation. Um, the architecture, a bit details about it. You can read about it. I'll of course have the links to the article as well that they have written, the white paper, I mean. But yeah, they build this 10 GPU segments, like individual segments, and that can be kind of that's the segments are kind of can be replicated across multiple AZs, and also they have a cold storage system for durability purposes, which is S3, which has like 9 nines storage system availability. So you kind of would never in thousands of years would lose your data. Um, and yeah, so basically it has all these cool architecture behind the storage system, so it leverages that for the database management system and also providing the consistency. That's where Aurora kind of comes and shines and kind of is super fast, and they have amazing claim numbers, and the claim is amazing based on the numbers that they say. And I personally also use Aurora in my day to day, so yeah, definitely one of the very cool design. um, and yeah, so this is an interesting part where it also, since everything was put on the network, right, there is a network IO bottleneck as well. Like, of course, our disk was slow, but then now you put a network, and it's not like network is crazy fast. It also has its own limitation. So this is where Aurora kind of shines, and it builds this redo log system. Redo logs are, instead of traditional logical or physical replication, redo logs kind of just provide the block level changes and like a simpler way to define what changed happened. And they have their own definition of redo logs, by the way. And these logs, the storage system kind of identifies these logs and understands these logs because it's separate. It can process these logs and make those changes inherent to the database that they have. Um, and so for example, let's assume from a writes perspective, something was written, insert into some table that is managed by Aurora, that the database. What it does is it writes to its own buffer cache first, the page that it needs, it retrieves from the network and all of it. And if it's in the buffer cache, it would update the store and it would write to the redo log. And now the redo log is replicated across the storage system as well as the read replicas that listen to the write system, right? So what really ends up happening is the replicas also have the rate state because they also put in the buffer cache. They also can kind of redo the changes that was done via the redo logs, and the storage system automatically does it asynchronously. This is the powerful performance benefit of it. It can do it asynchronously, commit to the actual disk on the storage system, and in the end, you have a consistent state because all the read replicas were also reading from the redo log, as well as the storage system was reading from the redo logs, and eventually you became like a consistent state with scalable system, right? So this is the very interesting part where it leverages the redo logs. It's super fast as well, and it decouple as I mentioned, decouple the computed storage, and you can still kind of get the read replica, and the latency between read replica and the actual master node is also really low because the amount of data is also not too much, because the storage again is separate, and you can also scale around based on AZs and how you define it. So let's say you are in Frankfurt and that system, the replica is also in Frankfurt, and you can leverage the Frankfurt storage system because it's replicated across multiple AZs. So the read replica can also just directly read from the Frankfurt storage system. It doesn't need to go to, let's say, New York storage system or Bangalore storage system, right? Like it is in that same easy. So that's where Amazon in general shines, the geographic scale that they have, and they also leverage this over there as well. So based on some numbers, it's amazingly fast. And sorry, and yeah, that's how it in general operates. Of course, I've not gone through a lot of details about it, but I will kind of giving a holistic overview of how it does. And as I was saying, like it has this multiple availability zones. Because of that, it captures all of this information much faster, and also is much durable. And yeah, you can kind of see how they can kind of scale, because they also have the ability to scale due to this geographic locations and data centers that they have. So yeah, the commit processing, as I was kind of saying, transactions start with the write operations in the primary instance. Changes are applied in the in-memory buffer cache and are recorded in val for durability. The val is the protocol, which is in the case of redo logs. In case of Aurora databases or MySQL database, because Aurora kind of primarily started with MySQL database. And then the asynchronous file streaming, this is the actual interesting part where it asynchronously tells the storage system to kind of capture this change. It does it change, commit it, and the read replicas are also simultaneously updated with the changes. Yeah, and then and the other aspects of it is that commit operation is marked complete once the val records are successfully replicated across scalable systems, which is across like the quorum, which is 4 out of 6, right? And so because of this being like each individual piece doing its own work in tandem with faster storage system, with faster read replicas and everything, it becomes super fast. There's no one single bottleneck. And also the quorum kind of defines it in a way where you don't need all the nodes, all the storage nodes to tell that it's consistent. Only 4 of 6 would work. And so that's the beauty of the design. And yeah, The other parts that I did kind of also mention is the data is consistent, the system is reliable, it's recoverable, it's fast, it's atomic. The transactions are also atomic, and all of it is captured without with having a really high potential scale that can have due to the scalable compute and scalable storage system. Um, so yeah, that's the performance. This so basically, I'll just quickly go and kind of uh, show you how the performance looks like, and one of the very interesting aspects of it is if you can see the write performance writes per second in a traditional MySQL system versus Amazon Aurora, like 1 GB. Uh, it made like it made like a 100,000 writes per second versus 8,000. For 10 GB, it also had similar numbers. For 1 TB, it was 41,000 writes per second. So this compared to MySQL, it's amazing how the performance looks like, or MySQL, traditional MySQL, I mean, because Amazon Aurora is built on MySQL as well. For number of connections, as we see, connections are also compute, right? Like these are fundamental compute that your service or application connects to database via some connection or connection pools, right? So it needs to kind of, it's if your compute is scalable, your connections can scale as well, and you can have more and more replicas, and your application is scalable as well, right? um, so Yeah. And the replica lag. This is also important aspect, right? Like, of course, if you were to like the, assume that with the cap theorem, right? In the end, like everything kind of is bound is by cap theorem, right? If you were to have no replica lag, then there's no way to do that. At least right now, it's practically impossible. You cannot have 0 milliseconds of replica lag. You will have something, but that's the trade-off. And that replica lag is so low that it really doesn't impact most of the majority of applications. From a read perspective, um, it's like you can just see the milliseconds, like versus a traditional MySQL master slave setup. This is super fast. It's like 2 milliseconds. Even current code base is super slow, slower than even access, like your in memory code base that lots of people write is much slower than the replication that it is. So in general, it's super fast. It's performant. And also it's multi-tenant, so you can have your even database system can have multiple tenancy of data layers, and you can build much more powerful applications on top. So yeah, that's the one second. I need to share the current. Yes, so there are some competition of Aurora database, which is um, NeonDB. There's one other new database cloud system in town. CockroachDB is also like similar in terms of scalability and aspect and all. It's not exactly the same, but it provides the scalable aspect similar to Aurora. There's Google Cloud SQL. There are other players in town, but yeah, that's pretty much how the whole relational online transactional databases are built with scalability in mind. And yeah, any questions? We don't have enough time, but I think I'm okay with one or two questions, and then you can kind of check in Taro, and you can use Taro's forum to ask questions, or just reach out to me. I will just put in my email over here. Yes, just feel free to unmute yourself and start asking questions.
Hey, this is Ankit here. I want to know like what does Aurora does differently than uh, Postgres or something like that. Is there any particular difference? Like, why should I choose Aurora or Postgres or any other RDBMS database?
So Postgres is it's a database system in general that is not. So it's, as I mentioned in earlier slides, like Postgres offers, like in your most of the applications, you don't need such scalable systems. Yeah? You can go with, in majority of the cases, you can go with a simple the EC2 instance running a Postgres server, and you're good, right? This Aurora kind of shines, and it also, you also have to pay for it, right? Like it's not cheap, but it also shines in aspect of the durability aspects, the fast creation of read replicas because the storage is separated. With a single server or even multiple replication servers with Postgres, you are bottlenecked with a the disk IO, right? Or even if it's SSD, it's the IO from the disk, right? Versus in case of a normal, in case of Aurora, that's the beauty of the system. So there is no one answer to what you should use or not. I use a lot of my traditional databases and my own server, and it works fine. I don't need Aurora. It's the use cases depends on your application, your scale, your growth of the company, what you're trying to do. Are you paying more money to just to avoid any avoid any failures or issues with your system when you don't want to manage it, all of it. So it depends. And also there are lots and lots of other challenges with managing your own database. So it's like giving money to manage the database and also get the scalability, uh, kind of. But yeah, there's no one single answer, to be honest. And also Postgres is the from a just to kind of give you one quick thing. We also the I mean Amazon also offers Postgres as a database system on top of Aurora's design on Aurora's architecture. So you can use Postgres' feature with Aurora's architecture in mind. So it allows you for durability as well as the features for Postgres. That is, it has a lot of other features which is far in terms of better than MySQL. So yeah, you can use MySQL or Postgres with Aurora. Yes, you can use MySQL Postgres. You can just check on Amazon's website, and they offer both of them. And we do use both of them, in fact, in my current company that I work with. Yes, go ahead,
Hey,
Ashwin.
Dharan, thanks for doing the talk. So expanding on that, sounds to me like I think what Aurora does a lot better is kind of having dedicated um, uh, like and a very optimized network layer to kind of like facilitate for faster reads, writes, and kind of replication. So, like, kind of if you were to put these things on a scale, like, on the in terms of like performance, it would be like open source Postgres on like lower ends. Like then you could kind of put RDS somewhere in between,
Yes.
which kind of is managed instances running Postgres, and then on the right would be something where like Amazon has its own infrastructure for like facilitating writes reads over like a highly optimized network layer to kind of handle like I think with those numbers that you shared, the sheer scale of like reads and writes across geographic replicas. So would you say networking is like the key thing here?
Yes, pretty much like what you said. You summarized basically the aspect, but pretty much network and the storage, like storage that they have built.
Mhm.
What is a traditional, let's say, server? Even if they are managing a traditional server, there will be an EBS volume attached to it, right? In case of Amazon, there's EBS basically is a disk, right?
Yeah.
So that's the volume versus a state storage. They have like a patent around that storage system or storage architecture that they've built, and it's far, I would say, far more durable and far more um, it's like a additional focus area. They don't focus on EBS volumes as much as they focus on the architecture and design of the system that they have built, right? Because that's a scalable storage system, which is not easy to build. Like scalable storage system is in general one of the hardest problems in computer science. So that's where they shine in general with the network, as you mentioned, and the storage system. But yes, like you can have your own local Postgres server and running without worries, depending on your application requirements, or managing it via EC2, or letting Amazon manage it via EC2, even before going to Aurora, because that's like an overkill in majority of the cases. But the design essentially is amazing to kind of understand.
Got it. One more question to kind of
Hmm?
ask. Talking about write ahead logs and I think what's called redo logs here. Um, do you or does anyone have like an idea of like what format does it look at, or is it like written in pure SQL? Like I'm assuming it's not pure SQL because that kind of like depends on the state of your system as well, like the number of records that would be modified with the SQL statements being executed. So I'm curious about like what um, so I think thinking about like assuming that the system state so far is consistent with all the replays of the write ahead logs above, you can kind of like reconstruct something more consistent. But I'm assuming because like thinking about the queries itself, right? Like I've seen database logs and like for SQL statements that get executed, like you can have like even for one SQL statement, you can kind of divide that into like multiple individual statements that get executed, and like for all of those they kind of specify which rows get updated for that specific query. So it can get really long is what I'm trying to say.
Yeah,
So
it actually depends, right? Like Postgres does it logical replication, as I mentioned. So they define a more high level because they allow for, let's say, if you want to have Postgres version 14 with Postgres version 15 as a read replica or something, or create replication between those two databases, it works completely fine because there's an abstraction. There's like a Python layer, just as, like from a language point of view, there's a Python layer instead of a C layer, right? Which
mhm,
needs to know the memory aspects of the system, versus Python doesn't really care. Uh, as in when you use Python, Python doesn't really care. It has an internal
mhm,
representation. So it depends how it looks like. Yeah, again, it depends on versions to versions how it is. But in terms of redo logs, it pretty much I would say it pretty much looks like which changes on which page, and with that page has of course a unique identification, and which page belongs to which block in the disk, and that's how the logs are kind of defined more on a it's more of a specific or more of a physical representation of what has changed in MySQL cases. But in Aurora cases, I'm not really sure how they define it. I think it's a little bit, I believe it's proprietary. I don't really know. But in most of the cases, Postgres, and you can check Postgres's log via some command, which I remember doing it a year back or something. So just to kind of try and see what exactly is happening with our systems, it was a issue that we had. But yeah, there are ways to look into it, but I'm not really sure how. Right now, I'm not really. I have the command in head to give
got
it.
it. I think what I understand out of that is that maybe like these database systems take a snapshot until like the periodic snapshots and write ahead logs are what kind of help with kind of bringing inconsistent systems back up. Like so like because write ahead logs can get really kind of long, there's like a sacrifice being made. Like when these systems come up, you have to read through all these logs to kind of reconstruct the database state. So maybe like what's used is a
So
combination of oh sorry, go ahead.
just one thing. This is again maybe a side discussion on things, and I think it's. I'll just take quickly few 1 minute or something, and we can stop. But Right ahead logs design is also very interesting. Just maybe read a little bit about it. But they have even in the disk itself, they define in pages, and there are like 8 KB of segments that is defined, or something like that around that. And then right ahead log has this cool feature of defining offset as the unique identification of what has changed in the point in time. So that
Mhm.
offset is also saved somewhere in the database system. And then whenever it goes up, when it comes up, it doesn't need to traverse through all the write ahead logs. It just needs to go to that file byte offset of the file itself, which is the actual physical representation of the point or the line in the file itself. Or like if you think of as a line in file, right? The offset itself is a unique identifier. So that's a very cool, interesting design element of the WAL protocol in general, which is being used by all the databases, I would say. So you don't need, like, the database doesn't need to read back the whole file in order to kind of redo things. It just has the reference to the oldest, the last offset that it committed, and the current offset, which is, and then it can just go and track the last offset without reading the whole file in memory or something. It just needs to kind of get that offset. And modern disks and modern file systems are really like, they allow for this fine grain byte reads, because they are also saved in blocks, right? So yeah, this one point I wanted to make across.
Yeah, yeah, for sure. Yeah, offsets. I think like these systems, they're kind of like used even in things like Kafka. Like they're kind of like used in those places as well, where you're kind of. I think those. Yeah, that's significant. Like that helps when there's like replica lag or like things like that, where you need to kind of for like maybe for like a couple of hours or something like that. That probably helps when, like, for those cases where like your instance totally is kind of like fried, destroyed, or things like that, where uh like maybe in the same offsets for those pages, like they don't logically point back to stored instances. Like for those, I'm assuming, like there are things like snapshots being used on top of which write ahead logs kind of like help fill in the, like the remaining
Yeah.
I guess gap. Is what I was thinking. I mean, this is, I've not read on it. I'm just curious about it.
No, I think it's a very interesting topic in general if you deep dive. But yeah, I think if anyone else has any questions, let me know, and just feel free to reach out on my email, as I mentioned. I can share the slides because I made sure that slides have all the content, just to kind of. Last time it was something that I had a problem with. So yeah, any other questions if anyone else has, and we can stop here. I guess we are about time anyways. So. If not, thank you so much for joining. Thanks.